Alright guys, so we are going to finish up our notes. We're on page 4 of our packets. Just a quick review, you can only use Fg equals mg, that mass times 9.8, when you know g. Okay, so that's in your packet, which is the acceleration due to gravity. So on Earth we know that it's 9.8 meters per second squared, and on the Moon it's 1.6 meters per second squared. So if you know that, you can do that to find the force of gravity, the weight. If you don't know g at a location, you're going to have to use our Newton's universal law of gravitation to find the force of gravity. Okay, so that's in your packet, at that location. So if we were on the surface of Jupiter, you'd need to use this to find Fg, the weight, or just the force of gravity between two objects. Alright, so let's try one of these. Calculate the force of gravity between you, 50 kilograms, and your shoulder partner, 60 kilograms, who is sitting 0.75 meters away from you. So this is solved out on here, but I kind of want to work it out so you guys can watch me do the math for it. So I've got my equation, which is Fg equals big G m1 m2 over r squared, and r is that distance between the two. So if I plug in my numbers, big G is 6.67 times 10 to the negative 11th. M1 is U, that's 50 kilograms. M2 is 60 kilograms. We're going to divide that whole thing by 0.75 squared. Okay, so when you put this in your calculator, 6.67 times 10 to the negative 11th, make sure you use that E button, that big E. Okay, multiply it out, and you should get 3.6 times 10 to the negative 7th newtons. Okay. So do that. Make sure you can prove to yourself you can get that on the calculator. And this is a very small force, right? 10 to the negative 7 is a small number, so we know that already. All right, let's try it now if you're doing it between you and your friend and you're sitting 6 meters away from each other. So now we're changing the distance between you guys. So let's go ahead and solve that one. I try this one on your own and then watch me do it. So big G m1 m2 over r squared. So I'm going to have the same number in the numerator, 6.67 times 10 to the negative 11th times 50 times 60. Now it's divided by 6 squared. Okay. So I put that in my calculator, and you should get 5.6 times 10 to the negative 9th. So this got a lot smaller. Okay, 10 to the negative 7, 10 to the negative 9th. That's a lot smaller just from moving 6 meters away. And that's because of this r squared right here. That makes it a whole lot smaller. So make sure you can get that on a calculator. All right, now we want to do between the Moon and you, okay? So between you standing here on the Earth, so here's me, and the Moon over there, which is 384,400,000 meters away, let's calculate the force of gravity between me and the Moon, because the Moon is pulling on me. So I've got big G m1 m2 over r squared. So big G is again 6.67 times 10 to the negative 11th. M1, which is me, 50. M2, the mass of the Moon, is 7.4 times 10 to the 22nd, divided by 384,400,000 squared. Okay, so I need to square that. So we're going to be dealing with really big numbers, so use those buttons in your calculator, okay? So use parentheses, do everything step by step was going to help you out, okay? You should get 0.00167 newtons. Okay, and that's bigger than your neighbor is pulling on you. So the Earth has more gravitational pull on you than your neighbor, which is kind of interesting. We're going to do a lab next week where we look at astrology and the planets pulling on you. All right, sorry this is a little off, but consider a 84 kilogram person standing on the surface of Earth. Let's use the simple force of gravity equation to find that person's weight force. So if we remember that, that was just Fg equals mass, it's supposed to be a G, times 9.8 So if we do an 84 kilogram person times 9.8 meters per second squared, we get 823 newtons. Okay, that's their weight here on Earth, that force of gravity pulling on them. Now what we want to do is do the same thing using our big G equation. And what we want to do is use the distance between them and the center of the Earth, which is 6,378,000 meters. And the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, not times 1,024, 10 to the 24th kilograms. So let's go ahead and try that. So big G, M1, M2 over R squared. So I do 6.67 times 10 to the negative 11th. M1, which is that mass of the person, 84. M2, the mass of the Earth, 5.98 times 10 to the 24th. So 4. Divided by that distance, which is 6,378,000 squared. Okay, don't forget the square there. And the crazy thing is we get 823 newtons again. I'm going fast because we're doing a video, but you guys should make sure you can calculate that in your calculator. But you get the same thing using either equation. Alright, so now the person is orbiting the Earth in a space shuttle above the Earth's surface. So now they're in a spaceship, and that is 354,000 meters above the surface of the Earth. So let's say this person has the weight of 823 from our last problem. Let's make a quick prediction about what this person's weight force will be in the orbit. Okay, so think about the video we watched. Are they going to have more weight, less weight? What do you think? So we're making a prediction. So in your packet it says to use Newton's, explain why we can't use the simple equation, so Fg equals m times 9.8. We cannot use that. The reason we can't use that, okay, we're going to cross that off, we can't use that because we don't know 9.8 that high above the Earth. So once you get up here, G is going to decrease, right? You're a lot farther away, so there's less acceleration due to gravity. So if we go ahead and work this through, okay, you do G, M1, M2, so you do the mass of the Earth, the mass of the person, divided by the radius of the Earth as well as that distance, so this total distance added together, and then square it. And you get a weight of 739.3 newtons. So some of you might have predicted that it would be 0, right? We thought weightlessness, but he still has a weight, a pretty decently big weight, right? So are you surprised to find that that weight is still pretty big is the question. And maybe you are, and we're going to talk a little bit about why it seems like they're weightless even though they're out there. So they still have that weight. Alright, so we just found that this 84 kilogram person has a weight of 739.3 newtons when they're the same distance away from the center of the Earth as astronauts orbiting the Earth. So use Newton's second law to find his acceleration if they were going to free fall down the Earth. So for that we're going to use F net equals ma. So if we know the only force on this guy, if I do a free body diagram for him, is Fg, pulling him down. So we know then his weight, which was 793.3, is equal to his mass, 84, times acceleration. You get an acceleration of 8.8 meters per second squared. So if he were to free fall from here down to the Earth, okay, this would be his acceleration. So it's still really close to 9.8, and that might surprise you because they still seem weightless out there. So we still haven't answered the question of why are astronauts weightless, but we do know they still have gravity, they have weight when they're out there, and if they were dropped, they would definitely accelerate down at a pretty high rate. So what is the weight for an astronaut orbiting Earth in a shuttle still so large? So why is that number still pretty large? And the answer is, from our perspective on Earth, it feels like the shuttle is really, really high. But from the perspective of the Earth to the shuttle, it's not very high at all, right? If this is the distance from the center of the Earth to the edge, going up to the orbit's not that much greater. And so it's only about an 1/18 of the Earth's radius. And so if we're only going up a little bit more versus coming from the center of the Earth out to the edge, we're going to not feel like our force is going to change that much. We haven't changed that distance enough to make a difference in that equation. Okay. All right, so you guys are done with your notes. Make sure you go over them, pause them if you don't understand. Sorry, there's bells. Have a great weekend. See you later.